front of it to stop it and make it bounce back again. But the last one was free to move on. When I threw this ball from my hand against the others, the one in front of it moved and hitting the third ball, bounced back again, and the third did the same to the fourth to the fifth, and so on to the end of the line. Each ball thus came back to its place and passed the shock on to the last ball and the ball to the bell. If I now put the balls close up to the bell and repeat the experiment, you still hear the sound, for the last ball shakes the ball as if it were a ball in front of it. Now imagine these balls to be atoms of air, and the bell your air. If I clap my hands and so hit the air in front of them, each air atom hits the next just as the balls did, and though it comes back to its place, it passes the shock on along the whole line of atom touching the drum of your air, and so you receive a blow. But a curious thing happens in the air which you cannot notice in the balls. You must remember that air is elastic, just as if there were springs between the atoms in the diagram. Figure 31. And so, when any shock knocks the atoms forward, several of them can be crowded together before they push on those in front. Then, as soon as they have passed the shock on, they rebound and begin to separate again, and so swing to and fro till they come to rest. Meanwhile, the second set will go through just the same movements and will spring apart as soon as they have passed the shock onto a third set. And so you will have one set of crowded atoms and one set of separated atoms alternately all along the line, and the same set will never be crowded two instants together. You may see an excellent example of this in a luggage train in a railway station, when the trucks are left to bump each other till they stop. You will see 3 or 4 trucks knocked together. Then they will pass the shock onto the 4 in front, while they themselves bound back and separate as far as the chains will let them. Next, the 4 trucks will do the same, and so a kind of wave of crowded trucks passes onto the end of the train, and they bump to and fro till the whole comes to a standstill. Try to imagine a movement like this going on in the line of air atoms, the drum of your air being at the end. Those which are crowded together at the end will hit on the drum of your air and ride the membrane which covers it inwards. Then instantly the wave will change, these atoms will bound back, and the membrane will recover itself again, but only to receive a second blow as the atoms are driven forwards again, and so the membrane will be driven in and out till the air has settled down. This, you see, is quite different to the waves of light which moves in crests and hollows. Indeed, it is not what we usually understand by a wave at all, but a set of crowdings and partings of atom of air which follow each other rapidly across the air. A crowding of atoms is called a condensation, and a parting is called a rarefaction. And when we speak of the length of a wave of sound, we mean the distance between 2 condensations or between 2 rarefactions. Although each atom of air moves a very little way forwards and then back, yet as a long row of atoms may be crowded together before they begin to part, a wave is often very long. When a man talks in an ordinary bass voice, he makes sound waves from 8 to 12 feet long. A woman's voice makes shorter waves from 2 to 4 feet long, and consequently the tone is higher, as we shall presently explain. And now I hope that someone is anxious to ask why, when I clap my hands, anyone behind me or at the side can hear it as well or nearly as well as you who are in front. This is because I give a shock to the air all around my hands, and waves go out on all sides, making it our gloves of crowdings and partings, widening and winding away from the clap as circles widen on a pond. Thus the waves travel behind me, above me, and on all sides, until they hit the walls, the ceiling, and the floor of the room. Wherever you happen to be, they hit upon your ear. If you can picture to yourself these waves spreading out in all directions, you will easily see why sound grows fainter at the distance. Just close round my hands when I clap them. There is a small quantity of air, and so the shock I give, it is very violent. But as the sound waves spread on all sides, they have more and more air to move, and so the air atoms are shaken less violently and strike with less force on your ear. If we can prevent the sound wave from spreading, then the sound is not weakened. The Frenchman Biot found that a low whisper can be heard distinctly for a distance of half a mile through a tube, because the waves could not spread beyond the small column of air. But unless you speak into a small space of some kind, you cannot prevent the waves going out from you in all directions. Try and imagine that you see these waves spreading all around me now and hitting on your ears as they pass, then on the ears of those behind you, and on in widening globes till they reach the wall. What will happen when they get there? If the walls were thin, as a wooden partition is, they would shake it, and it again would shake the air on the other side, and so anyone in the next room would have the sound of my voice brought to their ear. But something more would happen. In any case, the sound waves hitting against the wall will bounce back from it just as a ball bounces back when thrown against anything. And so another set of sound waves reflected from the wall will come back across the room. If these waves come to your ear so quickly that they mix with direct waves, they help to make the sound louder in this room than you would hear in the open air. For the ha from my mouth and the second ha from the wall come to your ear so instantaneously that they make one sound. This is why you can often hear better at the far end of a search when you stand against a screen or a wall than when you are halfway up the building nearer to the speaker, because near the wall the reflected waves strike strongly on your ear and make the sound louder. Sometimes, when the sound comes from a great explosion, these reflected waves are so strong that they are able to break glass. In the explosion of gunpowder in St. John's Wood, many houses in the back streets and their windows broken, for the sound waves bounded off at angles from the walls and struck back upon them. Now suppose that the wall were so far behind you that the reflected sound waves only hit upon your ear after those coming straight from me had died away. Then you would hear the sound twice, half from me and half from the wall, and here you have an echo. Ha ha. In order for this to happen in ordinary air, You must be standing